Section 2 of Familiar Letters on Chemistry. This is a LibriVox recording. LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by M.L. Cohen, Cleveland, Ohio, March 2007. Familiar Letters on Chemistry by Justice Liebig. Letter number 2. My dear Sir, in my former letter, I reminded you that 3 of the supposed elements of the ancients represent the forms or state in which all the ponderable matter of our globe exists. I would now observe that no substance possesses absolutely any one of those conditions, that modern chemistry recognizes nothing unchangeably solid, liquid, or aeriform. Means have been devised for effecting a change of state in almost every known substance. Platinum, alumina, and rock crystal, it is true, cannot be liquefied by the most intense heat of our furnaces, but they melt like wax before the flame of the oxyhydrogen blowpipe. On the other hand, of the 28 gaseous bodies with which we are acquainted, 25 may be reduced to a liquid state, and 1 into a solid. Probably, ere long, similar changes of condition will be extended to every form of matter. There are many things related to this condensation of the gases worthy of your attention. Most aeriform bodies, when subjected to compression, are made to occupy a space which diminishes in the exact ratio of the increase of the compressing force. Very generally, under a force double or triple of the ordinary atmospheric pressure, they become 1/2 or 1/3 of their former volume. This was a long time considered to be a law, and known as the law of Mariotte, but a more accurate study of the subject has demonstrated that this law is by no means of general application. The volume of certain gases does not decrease in the ratio of the increase of the force used to compress them, but in some, a diminution of their bulk takes place in a far greater degree as the pressure increases. Again, if ammoniacal gas is reduced by a compressing force to 1/6 of its volume, or carbonic acid is reduced to 1/36, a portion of them loses entirely the form of a gas and becomes a liquid which, when the pressure is withdrawn, assumes again in an instant its gaseous state. Another deviation from the law of Mariotte. Our process for reducing gases into fluids is of admirable simplicity. A simple bent tube, or a reduction of temperature by artificial means, have superseded the powerful compressing machines of the early experimenters. The cyanuret of mercury, when heated in an open glass tube, is resolved into cyanogen gas and metallic mercury. If this substance is heated in a tube hermetically sealed, the decomposition occurs as before, but the gas, unable to escape and shut up in a space several hundred times smaller than it would occupy as a gas under the ordinary atmospheric pressure, becomes a fluid in that part of the tube which is kept cool. When sulfuric acid is poured upon limestone in an open vessel, carbonic acid escapes with effervescence as a gas, but if the decomposition is effected in a strong, close, and suitable vessel of iron, we obtain the carbonic acid in the state of liquid. In this manner it may be obtained in considerable quantities, even many pounds weight. Carbonic acid is separated from other bodies with which it is combined as a fluid under pressure of 36 atmospheres. The curious properties of fluid carbonic acid are now generally known. When a small quantity is permitted to escape into the atmosphere, it assumes its gaseous state with extraordinary rapidity, and deprives the remaining fluid of caloric so rapidly that it congeals into a white crystalline mass, like snow. At first, indeed, it was thought to be really snow, but upon examination it proved to be pure frozen carbonic acid. This solid, contrary to expectation, exercises only a feeble pressure upon the surrounding medium. The fluid acid enclosed in a glass tube rushes at once, when opened, into a gaseous state, with an explosion which shatters the tube into fragments. But solid carbonic acid can be handled without producing any other effect than a feeling of intense cold. The particles of the carbonic acid being so closely approximated in the solid, the whole force of cohesive attraction (which in the fluid is weak) becomes exerted, and opposes its tendency to assume its gaseous state. But as it receives heat from surrounding bodies, it passes into gas gradually and without violence. The transition of solid carbonic acid into gas deprives all around it of caloric so rapidly and to so great an extent that a degree of cold is produced immeasurably great, the greatest indeed known. 10, 20, or more pounds weight of mercury brought into contact with a mixture of ether and solid carbonic acid becomes in a few moments firm and malleable. This, however, cannot be accomplished without considerable danger. A melancholy accident occurred at Paris, which will probably prevent for the future the formation of solid carbonic acid in these large quantities, and deprive the next generation of the gratification of witnessing these curious experiments. Just before the commencement of the lecture in the laboratory of the Polytechnic School, an iron cylinder, 2 feet and a half long and 1 foot in diameter, in which carbonic acid had been developed for experiment before the class, burst, and its fragments were scattered about with the most tremendous force. It cut off both the legs of the assistant and killed him on the spot. This vessel, formed of the strongest cast iron and shaped like a cannon, had often been employed to exhibit experiments in the presence of the students. You can scarcely think, without shuddering, of the dreadful calamity such an explosion would have occasioned in a hall filled with spectators. When we had ascertained the fact of gases becoming fluid under the influence of cold or pressure, a curious property possessed by charcoal, that of absorbing gas to the extent of many times its volume, 10, 20, or even, as in the case of ammoniacal gas or muriatic acid gas, 80 or 90-fold, which had been long known, no longer remained a mystery. Some gases are absorbed and condensed within the pores of the charcoal into a space several hundred times smaller than they before occupied, and there is now no doubt that they there become fluid or assume a solid state. As in 1,000 other instances, chemical action here supplants mechanical forces. Adhesion or heterogeneous attraction, as it is termed, acquired by this discovery a more extended meaning. It had never before been thought of as a cause of change of state in matter, but it is now evident that a gas adheres to the surface of a solid body by the same force which condenses it into a liquid. The smallest amount of a gas, atmospheric air for instance, can be compressed into a space 1,000 times smaller by mere mechanical pressure, and then its bulk must be to the least measurable surface of a solid body as a grain of sand to a mountain. By the mere effect of mass, the force of gravity, gaseous molecules are attracted by solids and adhere to their surfaces. And when to this physical force is added the feeblest chemical affinity, the liquefiable gases cannot retain their gaseous state. The amount of air condensed by these forces upon a square inch of surface is certainly not measurable. But when a solid body, presenting several hundred square feet of surface within the space of a cubic inch, is brought into a limited volume of gas, we may understand why that volume is diminished, why all gases without exception are absorbed. A cubic inch of charcoal must have, at the lowest computation, a surface of 100 square feet. This property of absorbing gases varies with different kinds of charcoal. It is possessed in a higher degree by those containing the most pores, that is, where the pores are finer, and in a lower degree in the more spongy kinds, that is, where the pores are larger. In this manner, every porous body, rocks, stone, the clods of fields, etc., imbibe air and therefore oxygen. The smallest solid molecule is thus surrounded by its own atmosphere of condensed oxygen, and if in their vicinity other bodies exist,